Hi, Honors Environmental Science, and welcome to the water cycle. In the PowerPoint, you'll notice that there is a states of matter animation. If you go to the URL, you'll be looking at this PHET website simulation. So I'll give you a moment to open that up. And if you'd like to do the questions on your own and then come back and look at my answers, then pause the video now and work through slides number 3 and 4 in the PowerPoint. All right, now that you've done that on your own, let's take a look at the states of matter. When you just naturally click in, you're going to be looking at neon. And number 1 says, describe the particles of the solid neon. How close are they to each other? Do they move? All particles move. It doesn't matter if they're a solid, a liquid, or a gas. So yes, absolutely, you can see that the particles here are vibrating. Now it says, describe the particles of liquid neon. If you notice, they all fall to the lowest level and they vibrate and knock against each other. Now, some of the particles are actually look like they're escaping, and this is because neon is a gas at standard temperature and pressure. Now, if we click a gas, you can see that the neon particles completely fill the container and spread out at an average distance from one another. Now let's go back and look at solid neon again. And let's compare that to water. Solid neon, solid water. Water is really a special case. If you notice, it has a lot more space between the particles. This is really unusual. Generally speaking, when things get colder, they get more dense, but water forms a crystal structure. And when it forms that crystal structure, it actually has these air pockets or this space between the H2O molecules. So this is going to lead to some pretty special properties of water. The property of water that's being shown here can be said in a lot of ways. It's why ice rises to the top of a lake or river. It's why it's so hard to freeze a large solid body of water, because once you get this solid top layer, the water underneath almost always, if it's deep enough, remains liquid for the entire season, allowing fish to survive. So this becoming less dense, floating to the top of liquid water property is incredibly important for environmental science. Now we're going to go back to solid water. Look back at solid water again. It has a fixed volume, shape, and mass. When we go to liquid water, it has a fixed volume and mass, but an unfixed shape. In other words, if I poured it into different containers, it would fall to the lowest level, but it would be able to take the shape of whatever container I put it in. Now we're going to go to a gas. When we get to a gas, we can see that just like neon, it bumps and jostles and moves itself across the entire space. Now go to the hot cold slider. I'm going to put it back into solid because this makes this a lot faster. And if I pull it to the bottom to cool, I'm going to tell you right now that getting to absolute zero is impossible. Now, you'll notice that the counter takes a longer and longer and longer time to extract the heat energy out of the water here, but the particles are never going to stop moving. Why is this? Because it's impossible to extract all of the heat energy out, or at least at this time in physics, we believe it's impossible. I'd like you to go back. We're going to go to back to neon, and we're going to put it in its gaseous form. Then we're going to take a look at argon, oxygen, and then water. And if you notice, gases generally behave very, very similarly, whether or not at room temperature they would be a gas like neon, argon, and oxygen, or whether they would be a vaporized solid, water. I'll let you think a bit about why this might be important to environmental science. Okay, in a moment, I am going to reshare my screen. Sorry, it's being a little fussy on me. Oh, good. There I am. Now I'm sharing my screen. Oh my goodness. Stop pausing my screen sharing. Sorry about that little technical difficulty. We're back to sharing. This is a summary slide. It is going to allow you to basically review what we looked at in the PHET animation. So I'll give you a moment to sort of be able to look at and take that in. Water on Earth. Water on Earth is primarily salt. If you look at a globe, that's something that's going to be obvious to you. They use the word saline because we're going to account for all salt mixtures. This would be something like an area where fresh and salt water mix, or like the oceans, which are all salt water. Freshwater. When we start to look at freshwater, what we realize is that it's actually an incredibly small percentage, just this little 3% here. As we look at the breakouts, it's going to appear to be 100%, but this pie chart here is only 3% of all the water. So it's 100% of the 3% fresh water. What you notice immediately is the vast majority of fresh water is actually unusable by humans on a daily basis. It's in ice caps and glaciers. Then you have groundwater. This is very useful to humans because if you have a well at your home, this is where you're going to be pulling it from. Surface water, lakes, ponds, rivers, all of those sorts of things. And other is going to be things like marshes, bogs, and other wetlands. Now, when we actually break this out again, the surface water out again, you can see that lakes are the vast majority. This was something that really surprised me because I think in the American Northeast, we have so many rivers, and I think we think of lakes kind of as farther away, like the Great Lakes, but they are the largest percentage of the 0.3% of water. And then, of course, you have swamps here at 11% and rivers at 2%. The hydrologic cycle. Obviously, nothing is ever created or destroyed. It just moves around Earth's biosphere. And this is done by the sun. The sun gives water the energy to evaporate, which then allows it to move through the water cycle. Here is a picture of the water cycle. There's not really a beginning or an end, but evaporation sometimes gets tagged as the beginning. And the reason it gets tagged as the beginning is because this is where that energy from the sun is allowing the water to move first. The other place where water is moving out is evapotranspiration, and this is through the respiration of trees. Essentially, when trees take up more water than they need, they will push that as a waste product during photosynthesis out into the atmosphere. Eventually, it will condense into clouds. Those clouds will then rain or snow in precipitation. That rain and snow will either infiltrate into the land or run off. Eventually, it will get to a body of water, either salt or fresh, and evaporation will happen again. Just so that you have some terms, I'm going to give you a moment to look at this. Unfortunately, we don't have flash animations anymore, so we're just going to have to kind of go through and take a look at what this would be like as a still photograph. When we up or raise or lower each of these factors, we want to take a look at what that does to evaporation. Now, wind. If I raise wind, Or in other words, I make it windier. Evaporation is going to happen faster. This is why you flap your hands when you put nail polish on. Temperature. If I raise the temperature, then I'm going to be increasing evaporation. Why? Because the air particles move more quickly, they bump against the water particles, and evaporation happens more quickly. Humidity. The higher the humidity, the lower the evaporation. Think about this. If you were in, say, an indoor pool, where the temperature and the humidity in the pool area is really high, and you get out of the pool and you stand on the deck and you talk to some of your friends and you realize 20 minutes later you've barely dried at all. That's because the air around you has so much moisture that the moisture on you does not evaporate. Now think another way. What if you were outside in the middle of August in the hottest, driest day ever? You might be dry in 5 or 10 minutes because evaporation is high and humidity is low. Transpiration. This is how plants let go of water. I'll be putting an Edpuzzle video up on this. So for any information on that, you can watch the Edpuzzle or YouTube video, whichever one I end up putting up. Respiration. This is what you do. Okay. This is the way that you put water and other gases back out into the environment. You breathe in, you take the oxygen, you breathe out, you exhale your carbon dioxide. And this is how you're able to run your body. Sublimation. In the water cycle, one of the odder things is sublimation. It's when objects go directly from a solid to a gas. And there is a video right here. So if you would like to, oops, sorry about that. The video is right here. If you would like to be able to go and look at that, then you can click on the YouTube link in the PowerPoint that is up online. Okay, this is another one of my animations that has sadly gone away, but we get to take a little bit of a look at infiltration. Again, there is one more video. So if you would like to go ahead and take a look at that, it is a YouTube video that will explain and show you examples of what I'm talking about here. The relationship between infiltration and runoff. That has a lot to do with soil. So when we look at soil, we have two things to talk about. What is the soil size? The bigger the soil size, the more space there is between. You can see how there's, I'm just putting a little bit of red here, there's space here. This means that when water falls, it will come and try to fill in these spaces. This is called infiltration. If the soil size is much smaller, it means the particles are closer together and water will run off rather than infiltrate. Infiltration is really good for us because it gives us this thing called a higher water table. Water table is what people and animals and businesses all use to get water if they don't have municipal water. So in other words, if you're on well of any kind, this is where you're getting your water. So when it rains, we don't want that water running off. If it runs off, it can pick up pollutants and it can go really far away. It can also erode things. Whereas if it infiltrates and goes into the water table, it's locked up there. Generally speaking, if the soil is clean, it's a really healthy water source for all of us to be using. And so that's why infiltration is so important. Here is groundwater. You can see that there are two ways. Infiltration is when it goes in. If there's a really high level of infiltration and the water table gets really high, you can actually have capillary action, which will put the water back up to the top. The water table, again, like on the last, is how high the water is. Anything below the water table is the zone of saturation. Anything above the water table is the zone of aeration. Please go through and watch this video, and then you'll be able to answer the questions on the next slide. If you need the answers to the last slide, they are in the notes section. Very last. This is going back to infiltration and runoff. When we have infiltration and runoff, this is where it's going to be really low. When you have grass on top of not terribly badly compacted soil, you can see that in here, this is where the water is running from here into this container, and the water's reasonably clean. When you go to the second one, I'm getting infiltration, but the water's dirtier because there isn't any plant matter on top to help clean it up. When I get to compacted soil with no plants on top, you are looking at the fact that I'm getting some infiltration, but some runoff. And you'll notice that this gets worse as I go along. More compacted, almost no infiltration. More compacted, almost all runoff. Until I get to no ground cover, heavily compacted soil, and I'm getting 100% runoff. Look at the quality of water that's running off. Nobody would want to drink that. If you had to drink one of them, I think everybody's picking this one because the infiltration allows the plants and other natural bacteria and items in the soil to clean the water up.